So today's topic is arcs and chords. We're going to learn lots about arcs and chords, some theorems and so forth. Take a look at the picture on the right. Can somebody tell me one of the arc in this circle? How about David? What do you think? TR. So arc TR, right? There's that part of that circle right up there, right? Very good. What about then a chord in this case? How about Narek? What do you think? RS. So this, which one is this the red part of the circle, or is it the segment RS? Segment is the core. You guys remember that? Right? Arc is the part of the circle. Core is the segment that has endpoints on the circle, right? So somebody read this for us. Nico, go ahead.
In circle O, shown at the right, RS cuts off two arcs.
Yep.
Arc RS and arc RTS. We speak of arc RS, the minor arc, as being the arc of chord RS.
And this is important because they could be talking about what is the arc of the chord RS. Are we talking about the major arc or the minor arc in this case? When they're talking about the arc of the chord, maybe the minor arc. Does that make sense? Because you could be talking about the other side, right? So it sort of is intuitive, isn't it? When we talk about the arc of this chord RS, we only think about that minor arc. That's what I'm saying. That's what we mean by the arc of the chord RS. Because guess what? In these theorems that we're going to be learning, they're going to be talking about the arc of the chord. Okay, does that make sense? Yes? All right, so let's look at our first theorem. Okay, let's move it up. Here we go. In the same circle, or congruent circle, here's what this theorem tells you. Congruent arcs have congruent chords. Not only that, the other way around is true also. Congruent chords have congruent arcs. Okay, so write that down and think about what this is talking about. And here's a picture of what we have here. Let's say that we have a circle O, and we have two chords, TU and RS. And of course, the arcs of the chord TU is right here, the arc TU, and then the arc of the chord RS is that RS, okay? What does it mean? Okay, so write this down. I'll wait and think about what this is talking about. All right, how about Hannah over here? Hannah, what do you think this is talking about? So let's just look at the first one first. So it says the congruent arcs have congruent chords. Of course, you have to have it in the same circle or congruent circle. So here, in this case, it's a congruent, same circle, right? In this same circle, what do they mean by congruent arcs have congruent chords? Yeah, so this one, the first one says what? Congruent arc. So guess what? The TU, the arc TU, this part of the circle. TU is congruent to what? The arc. The arc TU is congruent to arc RS. If that's true, what are they saying? Then the result is?
Chord TU is congruent to chord.
Exactly. Chord TU is congruent to chord RS. Very good. Does that make sense?
Yeah.
What about the other one here? What is this one saying? It's very similar to that, but it's the other way around. Jonathan? It says congruent chords have congruent arcs. What does that mean?
The same chords have the same arc, same length of arcs, like the same length.
Yeah, so in this picture, when they say congruent chords, what do they mean by this? What do you think?
TU and RS have
Yeah, the two.
same
Yeah, these two
arcs
segments.
as, like RT.
Yeah, so if TU, you see this chord TU? This chord, let's say if this chord TU is congruent to chord RS. What does that tell us then? If that's true, yeah, then these, you see the arcs that these chords make? Arc TU is congruent to arc RS. Does that make sense? So it works both way around. And it's kind of obvious as to why this might be. How did you go about proving this? Let's look at the first one first. If we have congruent arcs, we have our TU congruent to arc RS, what do we get? The chord, these segments, TU congruent to segment RS. How would you go about proving this? I want you to discuss this with your group. Go ahead, everybody. How would you go about proving this? Let's think about this. So, let me give you a little hint. Some of you needed some hint here. Here, take a look at this. Look at those dotted lines. So once you do that, right, that's a big hint. Look, they're gonna draw these auxiliary lines like this from the center to the endpoints of these chords. Okay. Okay, go ahead. How would you go about proving this? There's a hint. Okay, so is this helpful? I think this is a very nice hint. Okay, Jordan, what should we do here? So we're doing the first one. Congruent arcs have congruent chords. If in the same circle or congruent circle.
We know that arc T is equal to arc RS.
Yes, so we know that the two arcs are congruent. Yes, that's given. That's what they're saying. Congruent arcs.
You could draw auxiliary lines OT, OU, OR, and OS.
Yep.
OS, sorry. And they're all radii. So that
Good. What do you know about radii of a same circle or congruent circle? They're all congruent. So very good. Jordan, what do we do next?
And then since you know that arc T is congruent to arc RS, you can, and by definition of something, I don't remember what, you can conclude that angle TOU is congruent to angle ROS.
Yeah, angle 1 and 2 are congruent because these two arcs are congruent. Why is that? Very good, Jordan. Who could tell Jordan? Who could tell us? Grace, you remember why that was? Are these vertical angles? They don't necessarily have to be vertical angles. Okay, so that's good. A lot of people thought that these are vertical angles, but you know these two arcs, when they're congruent, they don't have to be like necessarily. I mean, it doesn't necessarily have to be that way, does it? Okay, so they could, but are they? Do they have to be? No. So it's not because the vertical angles are congruent. But Kenneth, you see why? What's the reason that angle 1 and 2 are congruent? Because if I could show angle 1 and 2 are congruent, because all the radius are congruent, it's really easy to show that the triangle is congruent. Because once the triangles are congruent, then the corresponding parts of congruent triangles, namely TU and RS, we could say that they're congruent. We're done. So all we have to show here is to show angle 1 and 2 are congruent. Kenneth, why would angle 1 and 2 be congruent?
Oh, because I don't know.
Okay, Kenneth, let me help you here. Do you know that we know that the two arcs, TU and RS, right? The red arcs, right? Okay, let's just hide this here. The two red arcs are congruent. How do you measure these arcs? Do you remember how we measure these arcs? Like if this TU is 50 degrees, okay? What do you know about this angle 2? That's 50. If RS is 110 degrees, what is this angle 1? 110, right? Do you remember how we measure these measure of an arc? How do we define the measure of an arc? It's from the central angle. And what do we know about these two arcs? They lie on the same circle. Not only that, these two arcs, TU and RS, are congruent. Okay, listen, if they are congruent, right? What do we know about their central angles? They're congruent because of definition of measurement of an arc. You guys remember that? Right? So therefore, angle 1 and 2 must be congruent. Would you not agree? By side angle side, the two triangles are congruent, and you could use the corresponding parts of congruent triangles are congruent. So you could say segment TU, which is the core, and segment RS, which is the core of this same circle, are congruent. Does this make sense? Yes? Alright, so that's how you go about proving that congruent arcs have congruent chords. The other way is very similar. If I knew that that you had congruent chords, then you could say the two triangles are congruent by saying side, side, side. Did you say side angle side? No, if I have congruent chords. In other words, if TU is congruent to RS, we know all radii are congruent. We know TU is congruent to RS, the two segments. By side, 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 the two triangles are congruent. So if the two triangles are congruent, what do you know about angle 1 and 2? They're also congruent, right? Because those are corresponding parts, which are the angles of the congruent triangles. Therefore, if these central angles are congruent, guess what? These two arcs are congruent by, again, definition of measurement of an arc. Right? Measurement of an arc is same as a central angle. Does that make sense? So it works both ways that way. Okay. So let's move on to then next thing we're going to talk about here. So do you remember midpoint of a segment? What's a midpoint of a segment? How do we define midpoint of a segment? Anybody remember? Yes, over here. Yeah, that point divides the segment into two congruent segments, right? Josh, what do you think a midpoint of an arc will be?
Divided into two congruent
Yeah,
arcs.
so very similar as that. So here is the definition of midpoint of an arc. It says point Y is called the midpoint of arc XYZ if, as we said before, these two arcs are congruent. Is that okay? Very simple. And of course, as just like a midpoint of a segment, any point, segment, or ray that contains Y bisects that ray, right? Just like that. It's the same thing for midpoint of a segment, right? So write that down. Very similar to midpoint of a segment. This is the definition of midpoint of an arc. Okay, so you should know that. Nothing surprising here. So here's our next theorem. A diameter that is perpendicular to a chord bisects. So anybody want to guess what we're going to say? Imagine a circle and a diameter. Okay? Can you picture that in your head? Circle and a diameter. Now draw an arc that is perpendicular to this diameter anywhere. Okay. But it's got to be perpendicular to the diameter. What do you think this diameter will bisect? Two people? Narek, what do you think?
The midpoint.
It'll bisect a midpoint? Doesn't make any sense. How do you bisect a point?
I guess.
Okay, good guess? Not quite. Yes, sir.
It bisects the minor arc.
It bisects the arc of what? That chord, right? Not only that, it also bisects the chord. So once you see the picture, Narek, it'll make here's the picture.
That was my sentence, yes.
Okay, good. But does this make sense? You have a diameter of a circle, right? And look at this chord that is 90 degrees, right? With this diameter. And look, guess what? AD, the arc AD and DB are congruent. Not only that, the segment AZ and ZB are congruent. Does that make sense? This is always going to be true. If you have a diameter and chord that is perpendicular to this diameter. And of course, how would you go about proving this? Any idea how we're going to do this? We're going to draw two auxiliary lines. Any idea how we're going to draw these two auxiliary lines? It's very similar to what we had before. Yeah, you make a triangle. That's right. So something like this. So that's your hint. As a group, think about how you go about proving this. It's very similar to what we just did before. All right, go ahead, everybody try. So this might be helpful to you. So here's what's given. Do you see what's given to you right here? You got a circle O, right? CD is perpendicular to AB. CD is your diameter. AB is your chord, right? If that's true, two things happens. The segment AZ is congruent to segment BZ, right? And also, the arc AD is congruent to arc BD, right? And here's, of course, how we're going to prove it. Think about how you would do this, okay?
So,
How about, what did your group say? David, what did your group come up with?
you said that the two triangles are congruent.
That's correct.
Hypotenuse leg theorem.
Yeah, because of HL, turns out these two triangles are congruent. Because once you have that, you're done.
Because OA is congruent to OB.
Good. OA and OB are congruent because radii of a same circle or congruent circle are congruent.
And OZ is congruent to
OZ is congruent to itself. So you have two right triangles, don't you? And the hypotenuse in the leg happens to be congruent, therefore two triangles are congruent. So what do we do next? Very good. Irene is not here. Sorry. And Madison, what did we come up? Yes. Which parts do we want them to be? AD and BZ are not corresponding parts of these two congruent triangles. Oh, AZ. Very good. So therefore, we could prove that, yes, AZ and BZ are congruent. We're done. Thank you. And also, then how are we going to prove that AD, the arc, AD and arc BD are congruent? How about, Leo? How do I show that? Okay, so we're good. It's really easy to show that the segments AZ and ZB are congruent, correct? Because the two triangles are congruent by HL. But what about the arc AD and arc DB?
Well, since angle 1 and angle 2.
Yeah, angle 1 and 2 are congruent, aren't they? Why? Because these are corresponding parts of congruent triangles, right? So you know then, by definition of measurement of an arc, these two arcs are congruent. We could also use some theorem that we used. Did you have? Can we use the theorem from before? I thought that too, but not really. If you look at the theorem before, we have two different arcs, don't we? Right, we have two. Here, we just have one arc, so it's not the same. But, does anybody remember this theorem from previous section? That the congruent central angles have congruent arcs? We could have used that, okay. right? But not the one before. I thought the same thing. I was like, couldn't we use this before, the one before? But this one describes, right? This one has two arcs, right? And two chords. This time we're just talking about one arc and one chord. So be careful. Is that okay? But like I said, you could use that theorem that the congruent central angles have congruent arc. You guys remember that? I think it was previous section. All right. So knowing this, we could do some examples. Let's try some examples, okay? Here we go. Go ahead, guys. Try this example one. Very straightforward. Don't look at the book because the book has the answers already. But take a look at this. How would you find value of x and y? Go ahead, everybody try. So knowing what we just learned from these two theorems, you should be able to figure out what x and y is. Okay. Go ahead. So I bet a lot of you were able to figure out what x is. How many people got x equals to 5? Raise your hand. That's pretty straightforward, right? Because what do we know? Just the theorem we just talked about, right? You have a diameter and a chord that's perpendicular. The diameter bisects the chord and the arc, right? So therefore, if this is 5, x has to be 5 also. Correct? The interesting thing is, how do you find y? By the way, why do they even have this? Do we even need that part, EF? Yes, we do.
Yes.
Okay, so it's not a trick question. You do need that information. How do we find y? Michelle, what would you do?
Well, chord EF is 10 units.
Yes?
AB minus 5, 10 units, which means
Good, hold on. So very good. EF, the chord EF is 10 units, right? The segment. Also is AB. Now, Michelle, what do you know about when you have two chords that are in the same circle that have congruent?
the arcs.
The arcs are congruent, right? The arcs of these chords must be congruent because these two chords are congruent. That's the very first theorem we talked about today, right, Michelle? So what's the answer for y?
43 degrees.
43 degrees is half of 86, correct? Because the CD bisects this arc in half. Excellent. So the answer is 43. How many people got 43 for this? Do you understand it now if you didn't get in for the first time? Does this make sense? Okay, you needed that information up there. They didn't just draw that for fun, right? Okay. Jordan asked, does this theorem, the last theorem, work for a radii that happens to be a perpendicular segment? The answer is yes, because if you were to extend radii, you get a diameter, right? Okay, good. All right, good question. Let's look at next example. Here we go. Example 2. It says find the length of a chord that is a distance 5 from the center of a circle with radius 8. Now, this is very interesting because we have to remember, look, if you have a chord that is distance 5 from the center. Center is a point, isn't that right? A chord is a segment. Do you guys remember how we define a distance from a point to a line or to a line segment? Who remembers this? How do we define the distance from a point to a line or line segment? Who remembers? Okay, Jocelyn?
The shortest one or the one that was perpendicular?
It is a perpendicular segment from the point to the line or line segment. You guys remember this? This is going to be crucial that you remember this. Go ahead and draw the picture also. See what you get and figure out the length of the chord. Go ahead, I'll wait. So let me give you a hint. Did you all come up with this picture? Because we said you got to have this kind of picture right up here, right? Because this is what we mean, okay? Because otherwise, right, you have to have the right picture. So you have to understand that this is what we're talking about, right? Okay, now it should be a lot easier now. So isn't this what we're talking about? Look, we got a circle, guys, and here's a chord that is 5 units away from the center. And remember that that 5 unit must be a perpendicular segment from O to, O to AB, right? So how do we find x? Because once you find x, you're done because the length of this chord will be twice of this x. Remember, we know this because of our previous theorem, right? We have a, just like Jordan mentioned, we basically have a radius, right, perpendicular to a chord. Well, this is really a diameter perpendicular to a chord, right? So who could tell me what to do here? How do I find the value of x? How about Shanna? What did your group come up with?
I did Pythagorean.
Yeah, you use the Pythagorean theorem. And when you do, what did we get using Pythagorean? Josephine, what did you get? Rad 39. And here's the work. Right? You just use a Pythagorean theorem. Yeah, so we're not done, are we? We have found the half of it. We have half the length. So, of course, the answer is what, class?
2 out of 30.
Okay. Of course, you have to. Because of the previous, right? OP, well, right, Jordan, this is the same question you asked, right? You look at the radius perpendicular to the chord. Yeah, it still works out, doesn't it? Because you could extend the radius, make it a diameter. All right, and with this example comes the next theorem. Think about this now. It's a nice sort of a transition. Here we go. Look at this. How about, who could read this for us here? Reagan, can you read this for us? It should be clear then. Thank you.
Figure 1.9. It should be there.
Uh-huh.
All the words within the circle above that are distance 5 from the center O will have within 2 red 30 centimeters.
Yeah, so look at this. If you, from this example, if I told you, right, that within the same circle or congruent circle, that I have a chord that has a length of 2 rad 39, what can you tell me about this chord in terms of distance from the center? It's always going to be 5. Does that make sense? You could actually imagine this chord moving around this circle, right? Does that make sense? If you were to move this chord around this circle, the distance from this, right, distance from the center to this chord is always going to remain as 5 units. Can you imagine the chord moving around within this circle, right? AB could be like this, AB, or here, right? You could actually move it, right? Or imagine a stick in a circle. You move that stick around in that circle. The distance is always going to remain the same. It's not going to be any closer or any further out, right? So guess what? Our next theorem is exactly saying that. So,
It's fun.
so here's the theorem. Narek, won't you read this for us?
Theorem 9.6. In the same circle or in congruent circles, 1, chords equally distant from the center or centers are congruent.
Yeah, and center is for if the two circles are congruent. So chords equally in a same, this is important. Of course, you have to have a same circle or congruent circles. Chords equally distant from the center, guess what? The length of these chords must be congruent, right? Does that make sense? The length are equal. The two chords are congruent, right? Well, would the other way around work also? In other words, congruent chords are what? Also equally distant from the center. Does that make sense? Yes.
Aren't those like basically like the converse?
Yes, they are.
So
Very good.
why don't they just say if it's only?
They could have, but they choose not to this time. All right, very good point. So if you happen to have chords that are equally distant from the center, they're gonna be congruent. In other words, their length are same. The other way around also, just like Josh mentioned, right? Congruent chords must be equidistant from the center. Of course, it's got to be in the same circle or congruent circles. Very straightforward, right? Do you see how that previous example really shows? It's a nice transition to this. So take a look at this example. This is very simple. If you have this picture, what can you tell me about? First of all, can we figure out what ST is? Yeah, because this is a perpendicular to this chord. Guess what? ST is 3. The whole thing is, this is 6. Guess what? How far is Q from S10? 4. You see how it uses the previous theorem there? Easy enough? So the answer for that is simply 4. Okay. All right. Are we good? Can you do something like this for your homework tonight?
Yes.
Very good. Okay.